Hello everybody, welcome back to Calculus 1 online at Frederick Community College. In this lecture, we will discuss a very important concept in the course, continuity. So here you see a quick outline of what we're going to discuss in today's lecture. First, we will talk about the three conditions of continuity, and we will go over some examples where we highlight each condition. Then we talk about what it means for a function to be discontinuous at a point, and we will discuss three kinds of discontinuity. Then we will finish our lecture with a discussion of continuity on the interval. Okay, let's go ahead and take a look at a definition of continuity at a point. We say that a function f of x is continuous at a point A if and only if the following three conditions are satisfied. First, we need to make sure that f of a is defined. Then we check that the limit of the function as x goes to a exists. In other words, we need to compute both left and right limit and make sure that they are equal. And then the last condition is that the limit is also equal to the value of this function at a. Okay, once these three conditions are satisfied, we can establish that our function is continuous at that point a. If one of these conditions is false, then we say f fails to be continuous at that point, so that means it is discontinuous at that point. All right, now you probably have an intuitive notion of continuity, and that is if you were to graph your function, you would never have to unattach your right and utensil, right? So you can just do it all in one move. And that is a nice way to think about continuity in a more informal way. So keeping that in mind, let's go ahead and take a look at the first example. Here we have a rational function 3x minus 2 over x minus 2, and you can see the graph of this function on the right side of the slide. The question is this function continuous at 2? Just by looking at the graph, we can see that the answer is no, it is not. Why is that? We have a vertical asymptote, okay, right here. This is x is equal to 2. That's our vertical asymptote. This is the value that makes denominator of this function 0. Okay, so which of the conditions is not satisfied? Well, we always start with the first one. Is f of 2 even defined, right? So is f of 2 defined? So you can pose this question right here. F of 2, does that even exist? Okay, and the answer is no. Okay, x is equal to 2 is not in the domain of this function. So the first condition is not satisfied. We do not need to check the other conditions. Okay, once the first one is false, we say this function is not continuous at x is equal to 2. And the reasoning is because it's not even defined at that value. Okay, so is it continuous? No. Which condition is false? 1. Condition 1 is not satisfied. Okay, so here is your definition, or rather a list of conditions that we need to check, and you will always be checking them in that order, starting with the first condition, then second, then third. Okay, and the first example where the first condition is not satisfied, we don't need to check anything else. Let's take a look at another example of a problem where we're checking continuity conditions. Here we have a piecewise defined function. It is negative x squared plus 4 for x less than or equal to 3. And it is a line for x minus 8 for x greater than 3. Here you have the graph of this function in Desmos, and on the right side of the slide, you can see how I am inputting my function into the Desmos calculator. Okay, so if you're interested in knowing how to graph functions that are piecewise defined, this is what you would do. Now the question is this function continuous at x is equal to 3? Now just by looking at the graph, we notice that there is this gap right here, right? There is a jump in the graph. So your intuition is probably telling you that this function is not continuous at x is equal to 3. Now let's go through the checklist, right? The continuity conditions. We always start with the first condition. Is f defined at that value? Okay, so f of 3 is defined. No issue here. What is it? So we'll look at our domain. Okay, so it is falling in this region right here. So x is less than or equal to 3. So we're going to plug that in into the first expression. So this would be negative 3 squared plus 4. And that, of course, is easy to compute. This is negative 5. So on the graph, it is indicated by this solid dot right here. Okay, so the first condition is satisfied, no issue here. Okay, once you check the first condition, let's move on to the next one. And that one was saying, does the limit exist? Well, let's see. The limit of this function as x goes to 3 from the left is negative 5. From the right, it is something different. It is 4. We can see it on the graph right here. Okay, we know how to compute those type of limits. So that tells us what? That the limit does not exist, right? So the limit as x goes to 3 does not exist because the two one-sided limits are not equal. Okay, that means condition 2 is not satisfied. So what is our conclusion? That means this function is discontinuous at x is equal to 3. So the answer here would be no. Okay, so here is your first example where the first condition is satisfied. Once we're happy with that, we'll move on to the second condition. The second condition is not satisfied because the two one-sided limits are not the same. We stop right here. We do not need to check the last condition. We can just conclude that the function is discontinuous at that point. Let's take a look at the next example where we're still checking continuity conditions. So here we just have a graph of our function f, and we would like to know if it's continuous at x is equal to 2. Well, let's go through the list. First, is f of 2 defined? Well, by looking at the graph, we can say yes, and here is the point that is equal to the value of the function. So is f of 2 defined? Yes, no problem here. We can say f of 2 is equal to 10. Okay, so this first condition, we are good to go. What about the limit? Does the limit as x approaches 2 exist? Well, let's take a look at the left and the right limits. So as we are approaching 2 on the left side, okay, looks like the function is going to 6. And similarly, from the right side, we are going to the same value. So does the limit exist? The answer is here, yes, no problem here. What is the limit? The limit is 6. Okay, so nothing surprising so far. So these two conditions are satisfied. We still need to check that the last condition is also satisfied if we want to show that this function is continuous. So is the limit equal to the value of the function at that point? And that one is a no. Okay, why is that? Well, what do we have in the first condition? 10. What do we have in the second condition? 6, and those two are certainly not the same. Okay, so this is a no. That means the function is not continuous at this point, so the answer is no. All right, so here's your example where the first condition is true, second condition is true, last condition is not true, so we conclude the function is discontinuous at that point. Okay, let's go ahead and review one more example where we're checking the continuity conditions. Here we have a rational function f of x is equal to x plus 10 over 3x plus 5. And we would like to know if this function is continuous at 0. So if you just look at the graph of this function carefully for x is equal to 0 and what the graph looks like, you can probably come up with the conclusion that the answer is yes, right? Just by looking at the graph and what happens to the function around 0. So let's go ahead and review the steps. Is f of 0 defined? Well, let's see. Can we plug in 0 into this function? So this would be 0 plus 10 on top, and then 3 times 0 plus 5 on the bottom. So 10 divided by 5 is 2, which does match our graph right here. So the answer is yes, there is no problem here. X is equal to 0 is in the domain of this function. We have no issue with this condition. What about the limit? Does the limit exist? Well, let's see what happens if we approach 0 from the left side. Okay, we are approaching 2. If we approach 0 from the right side, the function also approaches 2. So does the limit exist? Yes. Okay, no issues here. The answer is yes. The limit is equal to 2. You can just see from the graph. Okay, you could also create a table of values that x approaches to 0 from the left and the right, and plug that in and check. But this is fairly straightforward. Just by looking at the graph, we can see that the limit is 2. Okay, well, the last thing that we need to check is the limit equal to the value of the function at that point. And yes, 2 is equal to 2. Okay, this 2 right here and this 2 right here, this is what we're checking. These values are the same, so we now conclude that yes, this function is of course continuous. Okay, at x is equal to 0. All right, so your intuition might have already told you that just by looking at the graph. Okay, but this is how you would apply the list of 3 conditions. Okay, and it's not very complicated. So for cases when the function is continuous at a point, it almost feels like too easy, right? Okay, yeah, of course it's defined, the limit does exist, and the limit is equal to the value of that function. Okay, but that's how you would do it. Now that we have seen several examples of functions that are discontinuous at a point, let's go ahead and review 3 kinds of discontinuity. First, we're going to refer to as removable discontinuity, and that is the type when the limit of the function does exist, but it might not be equal to the value of the function at that point. So here you have an example where we have the left limit and the right limit, and they are equal. So the limit exists, but the value of the function could be somewhere here, or maybe over here, or maybe the function is not defined at that point at all. Okay, but the point is the limit does exist, and maybe that's the only condition that's satisfied. Okay, so that's what we're going to refer to as removable discontinuity. On the graph, you will basically see a hole in the plot at that point. Okay, let's take a look at the second type and this is what we're going to refer to as jump discontinuity, where we have one-sided limits exist, but they're not equal. So we've seen this example right here. So over here, the left limit is -5, the right limit is +4, right? So that is the example we've already discussed. The two one-sided limits do exist, however, they're not the same. So this is a jump discontinuity, and as you can probably see, the jump refers to this gap right here. Okay, so what about one more? Okay, this is what we're going to refer to as infinite discontinuity. And you can kind of think about having vertical asymptotes, right? So whenever we have a vertical asymptote, the limit of our function as we're approaching that value of a, either from the left or the right, could be either positive or negative infinity. So this is asymptotic behavior around vertical asymptote. So in this case, what would be the line over here, somewhere here? Okay, so at this point, what do we say? The function is not defined. So really, that's your first condition that's not satisfied. As far as the behavior goes, we have asymptotic behavior of a function around a vertical asymptote. As far as the limits go, what does that mean? Either positive or negative infinity. And that's why we say this is infinite discontinuity. Okay, so these are the three types of discontinuities that we will consider in our class. Now, let's take a look at an example where we're given a graph of a function and we would like to determine the type of discontinuity, if there are any. And here you have a bunch of points listed. Okay, so let's go through one at a time. For x equal to -6, what happens here? So -6 is over here. We can see that this is a vertical asymptote. Okay, the limit as x approaches -6 from the right is positive infinity. From the left, it's negative infinity. So this is infinite discontinuity. Okay, so the first one is done. Let's take a look at x is equal to -3. So that's this point right here. Okay, what do we have? We have the limit does exist, right? So the limit exists because the two one-sided limits are equal. They are equal to -2. However, the value of the function is something different. That's indicated by that solid dot. So the value of the function at -3 is 2. Okay, it's this value right here. So even though the limit does exist, the function is discontinuous at that point. What is the type here? This is what we refer to as removable discontinuity. Okay. All right, what about x is equal to 0? So x is equal to 0 over here. Let's take a look at the point. There's no issue here. X is equal to 0. This is where a function is continuous. Okay, so no problem. All right, what about x is equal to 3? So that would be this point right here. And we can see by looking at the graph what kind of discontinuity we have. We have jump discontinuity, right? So the left limit is -4. The right limit is +6. We have this big jump here. So this is jump discontinuity. Okay, and the last point, x is equal to 6. Okay, you can see by looking at the graph, there is absolutely no issue of continuity here. The function is defined at that point. The two one-sided limits do exist. They are the same. So the limit exists and the limit is equal to the value of the function. So this function is continuous at x is equal to 6. All right, so for this graph, we have 3 points where the function is discontinuous, and each of the types is also represented here on this graph. Let's do one more example. Similar to what we just did in example 5, we're given a graph of the function. We would like to determine the type of discontinuity, if there is any. Okay, so for x is equal to -6, let's identify that point right here. Looking at the graph, there's absolutely no issue here. So we say function f is continuous at x is equal to -6. Okay, no issues. All right, next point. What is it? -3. Okay, the function is defined, right? So the first condition is satisfied. What about the limits? Well, the limits are different. The left limit is -6. The right limit is +2. Okay, so this is where we have jump discontinuity. Okay, and of course the jump refers to that gap, okay, between the two branches. All right, x is equal to 0. This point right here. Let's see how the function is behaving here. Okay, the function is defined. There it is. F of 0 is equal to +2. What about the limits? Yeah, the limits do exist. Okay, the limits, the left and the right limits are equal to 6. Okay, but it's not the same as the value of the function. So this is what we refer to as removable discontinuity. Okay, x is equal to 3. So that point right here. Okay, what is our function doing for x is equal to 3? Okay, no issue here. Just like for x is -6, this is where f is continuous. Okay, no problem here. And one more, so x is equal to 6. Okay, same thing. Okay, there is no jump here, no asymptote, no hole. So the function is also continuous here. All right, so in this problem, we had 2 points where the function is discontinuous. We have a jump discontinuity for -3, and we have a removable discontinuity for x is equal to 0. Now, I would like to go over an example of a problem that you might encounter on your homework. And this one is a little bit of a critical thinking type of problem where we're given a piecewise defined function with an unknown variable, and we need to determine the values of this variable. So in this case, it's k, that makes the given function continuous at the point. Okay, so we have the following example. F of x is equal to x squared plus 4x plus 3 over x plus 3 for all values not equal to -3. Okay, and then it's equal to k if x is equal to -3. So you might encounter something very similar, maybe slightly different setup, but this is what you would do to solve a problem of this type. We need to check one condition at a time and then make sure that all of them are satisfied. So let's take a look at the solution to this problem. First, I'm checking if f is defined at -3. Okay, and yes, it is. F of -3 is k. Okay, we don't know what that k is. We need to determine all values of k so that our function is continuous. But the first condition is satisfied. Okay, now what about the second? We need to compute the limit. Okay, the limit as x goes to -3 of this function right here, and we do this algebraically. So what happens here if I plug in -3? I'm going to get 0 over 0. This is one of those forms that we refer to as indeterminate form. Okay, and at this point of the class, we know how to deal with it, and that is factoring. So notice that the next step for me was to factor my numerator. Okay, it factors out nicely. So this is x plus 3 times x plus 1 in the numerator. Denominator just stays as is, x plus 3, and we can cancel out this term right here. So now we have the limit as x goes to -3 of a linear function x plus 1, and we can just evaluate that at -3, and that turns out to be -2. Okay, so now we need to make sure that our function, the value of the function, is equal to the limit. Okay, and that's what condition 3 is. So I set this up. Limit of the function as x goes to -3 must be equal to the value of the function at that number, at -3. So what does that mean? F of -3 is equal to -2, and from here we conclude that k must be equal to -2. Okay, and if that is the case, then our function is continuous. All right, so once again, you might encounter a problem of this type, maybe slightly different function, maybe slightly different x. This is how you would approach it. Okay, let's go ahead and review our last example for today's lecture, and that is intervals of continuity. This is the problem I selected from your homework, so you might encounter something very similar to this, maybe slightly different graph. But here we're given a graph of a function, and we would like to determine the intervals over which the function is continuous. So to approach this problem, I would first identify all points where the function is discontinuous. So for our example, we have -6. This is where we have an infinite discontinuity, and we also have 0. This is where this function has a removable discontinuity. Now you might have an example where you have more than 2 points. No problem there. Just highlight all of them. Okay, and I'm going to make a graphical representation of what we're looking for. So let's go ahead and have this real line here, and I'm going to exclude -6, and also I'm going to exclude 0. Okay, so if I exclude those, now I can write my answer in the interval notation, and looks like NumAlta is also asking you to use commas to separate multiple intervals. So what are these intervals from a visual point of view? So it's going to be from -infinity to -6, and then from -6 to 0, and then from 0 to +infinity. Now, because we're not including these points, I'm going to write it out with parentheses around it. Okay, so this is what we do when we write out an interval and not include the and points. Okay, we're excluding both -6 and 0, and that's why we have parentheses around those points. All right, so this is going to be your answer for this example. So from -infinity to -6, and from -6 to 0, and then from 0 to +infinity. All right, we're going to go ahead and stop right here. Thank you all for watching. I'll talk to you next time.